So these are the last notes for chapter 6. We're no longer talking about the binomial distribution at this point. We've moved on to what is the geometric distribution. And geometric random variables are actually pretty similar to binomial random variables. Let's start with the conditions for a geometric setting. So the first condition, each trial in the experiment must have only two possible outcomes, being a success or a failure. The second one, the probability of success P, is the same from trial to trial. The third one, the trials in the experiment are independent of each other. And the fourth one, the variable of interest, our random variable that we're recording, is the number of trials it takes to get our first success. So the number of trials required to reach the first success. And the reason I put that one in red is because that's really the only difference in the conditions from the binomial distribution to now a geometric distribution. If you remember from binomial, the acronym we used was BINS. Well, this is really similar. For a geometric setting, all the letters are the same except for we can use a T instead of the N. So for a geometric setting, we can use BITS as our acronym for the conditions. So B stands for binary, that's the two possible outcomes, success or failure. I stands for independence. T just means trials until the first success. And then S, same probability of success for each event. So if you like using bins for binomial, you can use bits for geometric. So really the only difference then, a binomial random variable counted the number of successes and a fixed number of trials. A geometric random variable counts how many trials it takes to get our first success. And that's going to be our description for what is a geometric random variable. It counts the number of trials it takes for us to reach our first success. So what are the possible values of a geometric random variable? Well, it's still going to be something we're counting, so it's still going to be discrete. But keep in mind, we've got to have at least one trial to get a success, right? How many trials until our first success? We've got to have at least one trial. So the possible values of a geometric random variable, let's call it x, would start out as 1 being the lowest. You got to have at least one trial, or you could have 2 or 3 or however many it takes until you get the first success. So what are the parameters of a geometric distribution? And just as a reminder, if x was a normal random variable, the two parameters would just be mean and standard deviation. We're used to those. And then for binomial, it was n and p. So the notation for geometric, we could say x is a geometric random variable, and the only parameter we really care about is p. And p is just the probability of a success. So that's the notation. And the only parameter we care about for a geometric distribution is p, which is the probability of a success. I can't even begin to tell you what n will be in this case because I don't know how many trials it's going to take for us to get our first success. So example 1 has to do with Monopoly. It says, in the board game Monopoly, one way to get out of jail is to roll doubles. Suppose that a player has to stay in jail until he or she rolls doubles. The probability of rolling doubles is 1 out of 6. And I had to include the chance card for this example too. So hopefully we're all clear on what rolling doubles means. That means you roll the 2 dice and you can either get both of them 1s, both of them 2s, both of them 3s, all the way up to 6s. So the chance of you rolling any pair, or doubles as it's called, is 1 out of 6. That's the probability. So explain why this is a geometric setting. So you're in jail and you're rolling the dice and you're trying to get out. How many turns does it take you to get out? So we can use the bits idea. Let's meet each one of these conditions. So the B, the binary part, well, there's either a success or a failure. In this case, a success means you rolled doubles and you got out of jail. A failure would be you didn't roll doubles and you're still in jail for this turn. So the binary condition is met. You got successes or failures. And then we know the probability that you roll doubles is 1/6. So P, the probability of success, is still going to be 1/6 for all the rolls. So that means the S condition is good. Right? Same probability of success for all trials. We know that all the rolls are independent of each other, right? It's not like the dice remember what they were the last time they came up. So each roll does not influence the other, so the I condition is met. So independence is good. By the way, it wouldn't really make any sense here to mention the 10% condition. We're not sampling from some larger population, we're just rolling dice. And lastly, for T, well, we're interested in how many turns it takes for us to get out of jail. So we're counting the number of trials it takes for us to roll doubles and thus get out of jail in Monopoly. Part B asks us to define the geometric random variable and state its distribution. So I'm going to use X. If you want to use J for jail or something, that's cool too. And really what X does, it counts the number of trials it takes to roll doubles. So if I use the stats notation, I can say X follows a geometric distribution, and the probability of success, P, is 1/6. So that's a really succinct way to get that point across. And let's just make sure that we define what X is. X counts the number of dice rolls to roll doubles. Part C says find the probability that it takes exactly 3 rolls to get out of jail. And then we'll look at the case where it takes exactly 4 rolls. And here's what I love about geometric distributions, is the formula is actually really intuitive. So what's the probability that X equals 3? So 3 rolls to get out of jail. Well, that means that the first roll, you didn't get out of jail. And neither did the second roll. So the first roll would be 5 out of 6. You didn't get doubles, right? So if doubles is 1/6, then a failure is 5 out of 6. That's the first roll. And then the second roll, you fail again. 5 out of 6. And then just make sure that the third and final roll in this scenario is the one where there's a success. So then that's 1 out of 6. So if we multiply those 3 together, it's 25 out of 216, or 0.116 as a decimal. So there's really no fancy formula for a geometric distribution. It's just fail, 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 and the last one is the success. In this case, the success happened on the third roll. Okay, so how about for 4 rolls? What's the probability that X equals 4? Okay, that means on the first roll, it's a failure. So 5 out of 6, it wasn't doubles. The second roll, also a failure, 5 out of 6. The third roll, failure. And then just ensure that in this case, it's the fourth roll that we get out of jail. That's when our success comes in. That's where we have 1 out of 6. We multiply all 4 of those together and we get 0.096 as our decimal answer. And then part D says find the probability that it takes at most 3 rolls for us to get out of jail. So at most 3 rolls means that'd be the probability that X is less than or equal to 3, which accounts for all the cases where we get our success on the first roll. That's great. We get out of jail on the first roll. Or it takes us 2 rolls, or it takes us 3 rolls. So the probability we get out on the very first roll, like our very first roll is a success, that's actually pretty simple. That would just be 1/6, like it happens on the first roll. And then on the second roll, well, you have to go first roll is a failure times the second roll is the success. And then for the third roll, well, we've already done that one. It's 2 failures in a row and then a success. So if we add up each one of these cases, we get 0.421 as our decimal answer. So that's the probability it takes us 3 rolls or fewer to get out of jail in Monopoly, or in other words, to roll doubles. So the next part here says, in general, how can you calculate geometric probabilities? So if we have a geometric random variable X, and the probability of success is P, can you give me a general formula about how to calculate geometric probabilities? Well, we can. So what we've done so far, if I said, what's the probability that X equals K, or like the fourth roll, for example? All we do is take the probability of a failure, so if P is a success, 1 minus P is a failure, and we make sure that the first K minus 1 trials are failures. So for example, if this is the fourth roll I want to have a success on, that means the first 3 rolls are failures, and then the fourth roll I tack on is just a success, P. So if I want to know what's the probability my first success happens on the Kth trial, well, that means I have K minus 1 failures to start out with, and then my last one is that first success. Is this on the formula sheet? No, it's not. In fact, if you can just use intuition, you're going to be able to come up with this formula on your own anyway. So that should not be a concern for us. Just multiply by the first however many failures there are, and just make sure on the last trial you multiply by P, a success. The next question here says, on average, how many rolls should it take to escape jail and Monopoly? In other words, how many rolls should it take on average for us to get doubles? And if you think about it, you really have a 1 in 6 chance of rolling doubles anytime you roll the dice. So that means that on average, it should take us 6 rolls to get doubles. Sometimes a little bit more than that, sometimes a little bit less than that. But if you have a 1 in 6 chance to get doubles, that means that on average, it'll take you 6 rolls to see doubles. Okay, but do I have a formula for this? How do I know what the mean of a geometric random variable is? So the next part says, in general, how do you calculate the mean of a geometric distribution? Is the formula on the formula sheet. So if x is a geometric random variable with probability of success p, the mean of x, or if you want to call it the expected value of x, they mean the same thing, is just 1 over p. Well, that's actually the same result we'd get in the rolling doubles example. If you think about what the mean of x would be in this case, if we did 1 over p, which was 1/6, 1 divided by 1/6 would be 6 rolls for our average. Is that on the formula sheet? No, unfortunately not. So that's something that we have to use intuition for as well. In this case, if it takes us 1 out of 6 to roll doubles, then you can expect the mean would be 6 rolls to get doubles on average. Okay, so the final part of these notes starts out by asking, what's the probability it takes longer than average to escape jail? And then what exactly does that probability tell you about the shape of the distribution? So how long it takes you to escape jail, or how long it takes you to roll doubles, that's our random variable x. So we say x follows a geometric distribution with probability of success 1/6. Okay, we already knew that, and we just calculated the average number of rolls to be 6 rolls. So the expected value of x, or the mean of x, you could say, is 6 rolls. So let's calculate the probability and see what that tells us about the shape of the distribution. What's the probability it takes us longer than average, longer than 6 rolls, to get out of jail in Monopoly? Well, that's like saying the probability that x is greater than 6, more than 6 rolls. So for us to have more than 6 rolls, that must mean we had at least 7. So the equivalent form would be the probability that x is greater than or equal to 7 rolls. Because the next whole number above 6 would be 7 rolls. Okay, so there is a calculator command similar to binomial CDF that we'll use, but it will only calculate the things below a certain boundary. So if 7's our boundary, if we use the CDF command, it will calculate from 0 up to 7. So if we want to know what's the probability of getting something bigger than 7, we'll do 1 minus all the stuff below our 7 boundary. So we'll do 1 minus all the stuff that's 6 or fewer. So our calculator will actually calculate this for us. And the command, which you might have guessed if you looked around the calculator enough, it's not binomial CDF, it's geomet CDF for geometric CDF. And it just asks you, what's the probability of success, 1/6, and what's the x value you want to go up to, which is 6. So if we do 1 minus that answer, that leaves us with 0.335. So there's a 33.5% chance that it's going to take us longer than average to escape jail. Okay, so now the question is, what does that tell us about the shape of this distribution? Well, for something to be symmetric, you would think that it'd be about 50% above and below the mean. So that's clearly not 50%. So that starts to indicate to us that the shape of this distribution would not be symmetric. And therefore it couldn't be approximately normal or anything like that either. It's got to be skewed in one direction or another. Well, if we've got 33.5% of the area above the mean, that means that about 66.5% of the area, or over half, would be at or below the mean. So that kind of tells us what direction this distribution is skewed in. So this is the probability of taking more than 6 rolls, so that means that 0.335 represents the area above the mean. So there's not quite as much area above the mean as there is at or below the mean. There's 66.5% of the area below or at the mean. And one way we can figure out which direction it's skewed in is to compare the mean to the median. Now the median would be at the 50% area marker. So if the mean is below the median, right, the median would be the 50% mark for the area. It would be right skewed. But in this case, the mean is actually above the 50% mark. So we've only got a little bit of the area above the mean. That means the mean is somewhere above the 50% mark. So if the mean is greater than the median, that means this thing is right skewed. So if the mean is greater than the median, it's right skewed. If it's the other way, median bigger than mean, it's left skewed. And if they're equal, that's when it would be symmetric. But in this case, we know that there's only 33.5% of the area above the mean. So that puts our mean somewhere above the 50% marker or above the median, which means this is going to be a right skewed distribution. Okay, and let's try to illustrate this point. Let's start with a table of some values for rolling doubles. So it could take us 1 roll, 2 rolls, 3 rolls, and I'm going to use the decimal values for these. So for 1 roll, we know the answer is 1/6, right? 1 out of 6 on your first roll to get doubles. So that's 0.167 as a decimal. And then to take 2 rolls, that means you had 1 success and 1 failure. So we started with 1/6 for 1 roll. And then to get 2 rolls, our first one has to be a failure. So 1/6 times 5/6 gives us the probability of 2 rolls, which is 0.139. And then for 3 rolls, you had another failure thrown in there. So another 5/6 multiplier to get 0.116. And then for 4 rolls, you had another failure. So again, multiply by 5/6. I hope you're starting to see the pattern here. Every time I add a roll, it's 5/6 of the previous value. So the numbers are actually getting smaller. So here's 5 rolls, it's 0.08. And then 6 rolls is another failure included. So times 5/6 again, it's 0.067. 7 rolls. And then we'll take it all the way out to 8 rolls. Then after that, we're just going to put dot, dot, dot. I mean, we could stay in jail for a long time until we roll doubles, right? But the point is, how I'm calculating these decimals, every time I have to add a roll, I'm adding another failure before I get my success. So I start with 1/6, and every number is just multiplied by 5/6. So we said that the distribution, the graph of this thing, would be right skewed, right? So let's make a quick sketch of that. We'll put the x values on the x-axis. So we'll start with 1, and we'll go all the way out to 8. And then on the y-axis, we'll put the probabilities. We're going to make a histogram here. So at least we can just mark off like 0, and then 5, and then 10, and then 15. I know the highest one I have is 0.167. So I'll give you just a second to sketch those axes. And then I'll put my first bar here for my histogram. 1 goes up to 0.167, so just under 0.17, that tick mark. And then for 2 rolls, that's going to be a little shorter. It's 0.139, so I'll add that bar in here. And then for 3 rolls, it's 0.116. So what you'll start to notice visually is that each bar is actually 5/6 the height of the previous bar. They're getting shorter. So for 4 rolls, it's 0.096. For 5 rolls, it's 0.08. 6 rolls, 0.067. So it's actually a nice pattern here. Every bar is 5/6 the height of the previous bar. 7, 8, and it would keep going on and on and on. They would keep shrinking. But this does a good job of illustrating that this graph is definitely right skewed. And this applies to all geometric random variables. Their graphs will always be right skewed. And then I think an interesting question is, which roll are you most likely to get out of jail on? And you can see it here. You're most likely to roll doubles on your first roll as opposed to your 5th roll. So as far as which specific outcome is the most likely to yield a success, it's the very first attempt. Okay, so we talked about geometric random variables. I think the biggest takeaway and most important thing to remember is to multiply by however many failures there are up until that specific last outcome, that last trial, that has to be your success. All right, that's all for these notes. I'll see you in class.